Thank you, Martin. Thank you, Professor Romanowicz, and thank you, Alex, for inviting me. Actually, I've changed slightly the title of my presentation because I will mainly focus on the sensitivity of the deep seismicity after large and shallow earthquakes in the Japanese subduction zone. So first, I will briefly present the tectonic settings of the Japanese subduction zone. Then I will talk about the Ogasawara earthquake that Keiko Kuge and Zongwen also mentioned in their presentations. And then I will present you the consequences of the Tohoku earthquake in the deep seismicity. So the Japanese subduction zone consists of two slabs. So I'm not sure it works. No. Okay. So there is the Pacific plate that dives to the west. And above the Pacific plate, there is the Philippine Sea plate that dives to the northwest. So Japan lies above the double subduction zone. And the Pacific plate experienced two major earthquakes in the last decade. So there was the Tohoku earthquake in 2011 that caused many casualties, as you all know. And also there was the Ogasawara earthquake that occurred in 2015 at large depth. And it occurred in an area at that depth where there were no earthquake recorded before. And this is the seismicity that occurred 2 months after each of these earthquakes. So we see that the Tohoku earthquake triggered a large number of aftershocks. And it activated a large portion of the Pacific plate at shallow depth, from 0 to 150 kilometers depth. And the Ogasawara earthquake, so this is the data from the Japanese Meteorological Agency catalog. And in this catalog, for the Ogasawara earthquake in the south, there were only 4 aftershocks listed. So seeing this, one can only wonder if this feature is really something. I mean, if this deep seismicity, if this deep area is that quiet, and also what is the response of the deep slab to the Tohoku earthquake. So first, let's move to the Ogasawara earthquake. So this earthquake actually consisted of 5 sub-events that Ye and collaborators evidenced. So this is on the right, this is the moment rate function of these events, these sub-events. And on the left, this is the map view of these of the locations of these sub-events. So this event ruptured 40 kilometers by 50 kilometers area. And so, as I said, there was one main shock and only 4 aftershocks listed in the JMA catalog. And this is the traces of the P waves for all these events. So on the top, there is the main shock and all the 4 aftershocks below. The magnitude of these aftershocks ranges from 3.6 to 5.6. And so we used, to answer the question, is this area really quiet? We used these events as templates to apply a template matching technique. So we computed the coherency. So the coherency is a measure of how 2 waveforms are similar. And we computed the coherency on 3 frequency bands in the spectral domain over a 10-second long window that was sliding over 2 seconds. And for every, we kept the highest coherency value for these, in between these 3 frequency bands. And we had a selection criterion for the coherency that was the mean coherency plus 5 times the standard deviation of the coherency. And this is an example of one computation. So one computation is 1 template in 1 day of continuous signal. So this is the distribution of the coherency value. And the threshold for this distribution is given. It's just above 0.8. And also, we computed the difference between the matrix arrival times of the template and the matrix arrival time of the detected event. So, which is called d sub t here. So this is the equation. And let's say we have the template here in blue. So the template has defined matrix of arrival times that will vary according to the distance, to its distance to the stations. Let's say it detected this event here with a low coherency, and we compute, and so this distance will have also a given matrix of arrival times. Since this event is rather far from the template, then the d sub t would be large, sorry. And if there is an event close to the template, then the arrival times, the matrix of the arrival time will be similar, and d sub t would be small. So d sub t here is expressed in seconds, and if we know the velocity of the area, then we can use it as a proxy to express the distance between the detected event and the template. But we took a step further, and we created a new catalog of the events. And let's say we have a template I and a detected event J. And for at least 4 that was detected at least 4 stations, we computed the magnitude of the detected event by using the amplitude ratio of the events, of the waveforms. And also we located the events by double difference for the stations that detected J. So what we did here is that we used the travel time of the template to estimate the mean time of the absolute mean time of occurrence of the detected event, J. We use this absolute time of occurrence to estimate the new travel times of the detected events. And then we use these travel times to compute the double difference and in the end have the locations of the detected event. So we did it for 1 detected event and the 5 templates travel times. So we applied this method by using 47 stations in total. 46 of them are from the HiNet network with the sampling frequency of either 100 or 20 hertz. And there was 1 station used just above the area of interest, which is operated by GMA. And so this is the JCJ station. And here, so this is just to relocate, just to show you again the location of the main shock, and the other dots here are color-coded according to their depth, and we see that this event was really isolated at depth compared to the rest of the deep seismicity. So we applied it on 6 months of continuous data from February to July 2015 on the vertical component. And these are examples of detections. So on the top, there is the waveform of the template. Different example of detections. So this is a template. This is the waveforms at JCJ station. And so we see that the detected events, well, many of them can be buried in the noise level. But in the end, when we stack all these detections, we managed to find the P wave arrival of the template again. So now let's have a look at our new catalog and how the seismicity evolved with time. On the top, this is the cumulative number of events that we detected. So in total, we detected 58 events. So that includes the 5 templates. So in total, 53 new events were detected. And remember that we did this analysis for events detected at least 4 stations, so either accounting for JCJ, this is the blue line, or without JCJ, this is the orange line. And the magnitude of the events are shown here on the bottom of the slide, and the distribution is on the bottom right. So we see that the events were mainly magnitude 3. And the distribution of the coherency gives that the coherency was mainly between 0.8 and 0.85. And that is rather interesting because there were no high coherency values found in this analysis, so no highly similar earthquakes were found, like for example repeating earthquakes, so there were no repeating earthquakes in this area. So remember that we computed the d sub t in seconds, and now we will see how the events behavior is, how the events behave according to their d sub t values. So if we take, for example, the d sub t smaller than 25 seconds, so these are all the lines in the continuous lines. The events seems to have a rather similar behavior with the fact that there is an acceleration phase from the 16th of February to the 18th of May here. And this acceleration is followed by a quiescence phase that lasted 12 days just prior to the main shock. Then all the events see a decay, no-more decay that we can fit with a p-value of 0.97. And on the contrary, events that had a d sub t superior to 25 seconds don't see the acceleration, neither the Omori decay. So for the rest of this part of the talk, I won't consider them. So now let's have a look at the event's location. On the left, this is a map view of the locations of the events. The white star indicates the location of the main shock. And actually, the aftershocks that we used as templates are located really close to the main shock. And on the right, this is the cross-section view. The color of the dots indicate the value of the d sub t in seconds. So we see that the value of d sub t decreases when we get closer to the templates. And the events seem to be aligned along a east-west line. Let's see now how they are located with the time. So the color of the dots now indicate their time of occurrence. The first one on the left shows the seismicity that occurred in the first 2 months of our analysis. And we see that there are only a few earthquakes. And in the middle, this is 2 months after. So this is the phase, the acceleration phase that we see. And also, it seems that the seismic events tend to move towards the east direction. And the final plot here gives the location of the aftershocks of the Ogasawara earthquakes that we detected. And we see that there are many events east to the main shock. What can these events tell us about the geometry of the slab? So this figure was presented by Keiko Kugie, but I will briefly talk about it. So these are the tomography pictures that Obayashi and collaborators presented in 2017. So these are cross-sections. So every cross-section is shown on the left here, the locations. The top left side shows the northern cross-section, and the bottom right side, the southern cross-section. And actually, we see that in the north, the slab plunges to the west underneath the Philippine Sea Plate. And in the Ogasawara earthquake area, so this is the panel E on the middle top, the slab changes direction and plunges vertically, and then going to the south, we see that there is a rollback of the slab. So the slab actually plunges to the east at the south of the Ogasawara earthquake. This can be easily explained by the work of Schellart and collaborator, who they measured the velocity of the plates of all the subduction zones in the world, and they shown that the plate velocity in the Usebonin area is 8.2 centimeters per year. And what is really interesting here is that the trench direction for the Izubunan area is the same as the plate, so it goes to the west. And actually, when we go up north to Honshu and then to Hokkaido, this velocity decreases and changed sign to go to the east again. So this, the Izubunan slab and this area of Ogasawara is really at the limit of the behavior of the changes of direction of the slab, of the trench, sorry. And so now let's have a look at the detected events at depth and the distribution at depth. So again, the time, the color gives the time of the events, and there, the size of the dots indicates, well, it's proportional to the magnitude of the events. So the large yellow circle indicates the main shock, and the smaller yellow circles indicate its aftershocks. And the rest is our newly detected events. The gray dots also, what I didn't say is the seismicity for 2015 for this area. And this is an east-west cross-section. We see that the seismicity can be divided in 3 groups. So one shallow, one at depth of between 460 and 600 kilometers, and another one at just above 700 kilometers. So let's now image the discontinuities. So there is the 410 kilometers discontinuity and the 660 discontinuity. And we can hypothesize on the geometry of the metastable olivine wedge here. But just to precise, so this is a projection of all the seismicity. And actually, when we look in the north-south cross-section view, we see that the detected events are well aligned along a thinner plane here. This plane is thick of around 50 kilometers. And we see that there are mainly small events of magnitude 3 that are concentrated, and then the main shock occurred with its aftershock. This configuration of the seismicity that is concentrated on a thin plane is really coherent with the model that Zhongguenzhan presented in his article of 2017 for one slab, where we see that there is a thin line of probably where the transformational faulting can occur. So as a start of the rupture of deep earthquakes, and then it can extend outside the mantle olivine wedge by either passive or active processes. So just to conclude on this part, so we detected 53 events using the template matching technique. The events see an acceleration of the seismicity followed by a quiescence prior to the main shock. And they also follow an Omori decay. Their location is really helpful because it indicates the rollback of the slab really clearly, and also it highlights the geometry of the metastable olivine wedge in this area. When I started this analysis on the Ogasawara earthquake, I first looked at the seismic catalog of the GMA catalog. And I saw that the Tohoku earthquake affected this seismicity, this very deep, the deep seismicity in this area. And I extended this analysis towards for the entire Pacific subduction in the Japanese subduction zone. And that is what I'm going to present you now. So just a reminder that the Tohoku earthquake occurred here in the north of Honshu. So it triggered large co-seismic and also post-seismic slip, which is also due to its large magnitude. But also, before the event, actually, there was a gravity anomaly. So this is the left panel here. This is a work done by Isabelle Panet and collaborators in 2018. And they evidenced that there was a gravity anomaly that preceded the main shock. And actually, this is something that tells us that there is something, well, there was something going on at a long wavelength scale before the earthquake. So why not after the earthquake? I defined several, all the areas of interest along the Pacific plate at depth. So to do so, I defined reference points, and I selected seismicity that was inside a certain aperture angle from these reference points in the strike direction of the plate. And the seismic events here are deep, from 350 to 700 kilometers depth. And I used the data from 2000 to 2018 with a magnitude of completeness of 3.7. So here is the GMA catalog. I computed a linear fit on the data before and after Tohoku earthquake, and I've analyzed the rate change in percent of this seismic rate. This is the result. The dots indicate the seismicity for the period of analysis, and the color gives the changes of seismic rate after Tohoku. So to clarify this, I will now we are going to travel along the Pacific slab, and just mind you that here all the area experienced a negative change of seismic rate except the Tohoku area. So I'm going to present this. So first, the Ogasawara area here experienced a change of slope of 8%. So we see the previous, the pre-Tohoku seismic rate was of 45.4 event per year, and it changed to 41.8 event per year. And this change is rather robust, and it lasts in time, since it lasts until the end of the catalog analysis. Now going up north, there is also an even greater change here of seismic rate in the area just south of the Tohoku earthquake. So the change here was experiences of 30%. And on the contrary, in the Tohoku earthquake area, so below the Tohoku earthquake, there were no change of seismic rates. So one can wonder if this is due to also the value of the magnitude of completeness. So I've looked at different magnitude of completeness in the JMA catalog. And mind you that the scale here is changed to easily compare the different magnitude of completeness. So on the left side, this is a magnitude completeness of 3.7, the one that I've shown you just before. On the middle, this is a magnitude completeness of 4, and on the right, this is of 4.5. And what we see here is that the area in the south of Tohoku experienced a negative change of seismic rate, and this is seen with all the magnitude of completeness. So this change is really robust, and it lasts in time. In the Tohoku area, well, at least below the Tohoku area, there was no change of the seismic rate at depth. And in the north of Tohoku, the change also is robust until the area that is really up north at the limit of the analysis, where the change is not really robust. So we think that it's the limit of the Tohoku effect in its extension. So here the Tohoku affected the seismicity, the deep slab, in the deep slab, for 1,000 kilometers up north to 1,500 kilometers to the south. So I'm really sorry because the colors are not really clear. But, so this decrease in seismicity is really robust, and so it affected the deep slab seismicity. And it's particularly clear in the north and south of the Tohoku, but not just below the Tohoku earthquake. At first order, we can maybe think that it marks the slab velocity, so maybe there is a slab that slows down, or is it due to a viscoelastic stress transfer or other effects? So we are really open to discussion because this really is puzzling. Yeah, feel free to. General conclusion. So 3 main points. The slab at depth is far from being quiet. And so we saw that with template matching, we can really increase the number of events in the catalog. And also the newly detected events helped us in defining the geometry of the slab and the mental living wage geometry. Also, there are interactions between deep parts of the slab and shallow parts of the slab. So this is something that we really need to consider when studying the seismicity of subduction zone. So maybe I'm stating the obvious here, but we really need to see the big picture because there are earthquakes from 0 kilometers to 700 kilometers depth, and they all matter. And thank you for your attention.